Hello and welcome to lecture 7 on the course on quantum entanglement and non-local games. This is the third part of the lecture on rigidity of CHSH games. We have already completed the proof, but we left a couple of lemmas which we are going to finish today. So the first lemma which we used was as follows. So suppose psi in CD tensor CD has full Schmidt rank and A and B in CD cross D be unitaries such that A tensor I acting on ket psi equals to I tensor B acting on ket psi, then A must be B transpose. So we are going to prove this lemma now. Okay. So the proof is as follows. Let ket psi, which equals sum over k from 1 to d lambda sub k k ab be the Schmidt decomposition of psi where lambda 1 is greater than equal to lambda 2 greater than equal to lambda d, which is strictly greater than 0. Then, so here we could have assumed that the lambda d is greater than 0 because psi has full Schmidt rank. Okay. Then in this case, A tensor I acting on ket psi is going to be sum over k lambda k A acting on ket k tensored ket k in the Hilbert space B HB. So this is what is A tensor I psi is going to be, and I tensor B psi, if I calculate this quantity, here also we are going to have a summation, but now I have sum over k lambda k ket ka tensored bk on B. Okay. So this is a valid decomposition because A and B are unitary. So let multiplicity of lambda 1 be R. So then what we are going to have is that now from the Schmidt decomposition result, we know that the subspace associated with the given eigenvalue is unique. So since now ket 1 up to ket R are all subspace are all eigenvectors which are associated with the lambda 1, so they have to be the same. Okay, so now if we look at A tensor I psi, since A is unitary and B is also unitary, so AKs are also orthonormal vectors. Since AKs are orthonormal vectors, this is actually indeed a Schmidt decomposition of A tensor I psi, and this is going to be a Schmidt decomposition of I tensor B psi. So if we look at the subspace associated with lambda 1 here, right? So it's like A1 A tensor 1 A2 A tensor 2B A3 A tensor 3B up to so on up to AR A tensored RB. Okay. So here the subspace associated with lambda 1 in A tensor I psi subspace on, let's say, on HA, right? So this equals what? A1A up to ARA. So the span of this set. Now this must equal the subspace associated with lambda 1 in I tensor B psi, right? So this has to be equal to span of 1A up to RA, right? Because the subspace is unique. Now similarly, if I look at the HB part, so with associated with A tensor I psi, I have the vectors associated with lambda 1 as 1B tensor RB. So I have that span of 1B up to RB. This is going to be nothing but B1B up to BRB. So these two spans are also going to be the same. Okay. So what is happening now is that when A acts on ket 1 up to ket R, then it essentially leaves this space as invariant. And similarly, when B acts on ket 1 up to ket R in the B space, in the HB space, then it leaves the same space invariant. So therefore, we have that 1A up to RA, the span is invariant under A, and 1B up to RB is invariant under B. So on. So actually, in fact, we just did this for lambda 1. You can actually do it for the next lambda R plus 1, the next distinct eigenvalue, and so on. So here what you will get is that you will get a block decomposition of A as A1, and then there will be a block of A2 up to so on, and then finally we will have some block, say A, maybe let me use the variable, say AL. Okay, and correspondingly for B also. So lambda 1 up to lambda L, if I have L distinct eigenvalues, then I am going to get L such blocks. So for B also I am going to get these L blocks. On each of these blocks, I have the same value of lambda acting, same value of lambda in the Schmidt decomposition corresponding to these orthonormal vectors. Right. So let's work with the first block. So working with the first block, what I have is that, so let me see how this A matrix changes the psi on this particular block. So since we have seen that the blocks do not interact with each other, so I can just take the first R vectors, and what I can now compute is the component of psi along the first R vectors. So what is this going to be? This is going to be lambda 1 times sum over k from 1 to R, A1, Ka, tensor Kb. This equals lambda 1 sum over k from 1 to R, Ka, tensor Kb. Right. So what I'm going to get then is that A tensor I acting on psi maximally entangled, A band tensor I acting on psi maximally entangled equals I tensor B1 acting on psi maximally entangled. So this is maximally entangled on R dimensional spaces, right? Because I have sum from 1 to R. So because here it's, I can just cancel off lambda 1 and lambda 1, and now it appears that A1 tensor I is just acting on sum over k, right? And I can always normalize by 1 over square root r, so it will be like A1 tensor I acting on psi maximally entangled, similarly the other way around. Okay. So these two vectors are actually going to be equal, and these are also unitaries, so these are of unit magnitude as well. And now if I take the dot product between them, psi A1 tensor I, let me just say a dagger also, I tensor B1 acting on psi, again maximally entangled. So since these two vectors are actually equal, and both these vectors are of unit magnitude, so essentially this will be the norm of any of these vectors, and norm is going to be 1 because psi is of norm 1, psi maximally entangled is of norm 1, and unitaries don't change the norm, so this has to be equal to 1. But now if you recall, we actually did a result wherein we said that okay, so first I can write it as psi A1 dagger tensor B1 psi equals to 1, and now if you recall the result for maximally entangled state, we have that this must be equal to 1 over d times trace of A1 dagger B1 transpose, right? This must equal 1. And if you now consider this as the Hilbert-Schmidt inner product on matrices, so this is nothing but the inner product between A1 and B1 transpose. So this inner product is going to be D, and D is nothing but square root of the inner product between A1 and A1 and B1 transpose and B1 transpose. Why is it so? Well, so each of these AIs which we had just so defined, these were actually unitaries, and hence even on the reduced subspace they act as unitaries. And if I now take A1 dagger A1, then I'm going to get like identity, and then trace of that identity is going to be D. So this thing and this thing are both D, or right. So here actually D happens to be R, so I should have used R everywhere because we are just taking the first R components. Yeah, so this happens to be R, and this happens to be R. And this also happens to be R, right? So just verify that these inner products are also R, because these are actually acting on, these are unitaries on R dimensional spaces, and then trace of A1 dagger A1 is then going to be trace of identity on R dimensional space, and trace of identity on R dimensional space is just R, so this is also R, and square root of R times R is also R. So now again we see that by Cauchy-Schwarz inequality, we should in general we have an inequality between the term on the left and the term on the right. This holds as an equality if A1 is proportional to B1 transpose, right? So which means that B1 transpose is proportional to A1. So this is by Cauchy-Schwarz inequality, or B1 transpose equals to alpha times A1 for some scalar alpha. Now for this particular value of alpha, the inner product between them is going to be alpha. And we have just seen that, or rather alpha times R, but it happens to be exactly R. So what we are going to get is that alpha is 1, right? Because these are essentially unitaries, and unless alpha is 1, this product will not be equal to exactly R. So hence we get that A1 is essentially B1 transpose, or A1 transpose is B1, and we just did this analysis for the component along the first eigenvector lambda 1, but in general also we can do it, and then overall for each of these blocks which we have decomposed A and B into, the two corresponding blocks will be transpose of each other, and then overall, since these are just diagonal blocks, what we'll get is that A transpose equals to B. So B is A transpose. Right. So this is the first lemma we used, and note that here we have been using the one of the three lemmas which we did in the first lecture, right? So when we did that if you sandwich between two psis A tensor B, then you are going to get trace of A transpose B over D, right, in the D-dimensional space. So we have used that lemma which we did in the first lecture. So as you see, we have used all these lemmas quite often. Okay, so this finishes, and the reason why I needed to do this was because in the last lecture we have used this lemma already, that in such a case then A transpose has to be equal to B if A tensor I psi equals to I tensor B psi. So this lemma we have now proved. Another lemma which we also used in the last lecture was about these anti-commuting operators. So let's prove that. So this lemma says that if A and B are binary observables such that AB equals minus BA, then there exists a basis such that A is X tensor IM and B is Z tensor IM. Okay. So here the crucial thing is that they are indeed binary observables, right? So since these are essentially, since A is binary observable, it is Hermitian with eigenvalues in plus minus 1. Okay. Therefore, there exists a basis where A is actually IM1 and minus IM2 for some M1, M2, right? So there are, I have just collected the eigenvalues plus 1 together and the eigenvalues minus 1 together. And under this basis and under this sort of block decomposition, I can also write B as B11, B12, B21, B22 under this basis decomposition. Now let me use the fact that AB equals minus BA. So if you just do this calculation and you compute AB and BA, you will get that AB actually equals B11, B12, minus B21 and minus B22, and this equals negative of BA, and if you calculate that, that will turn out to be B11 minus B12, B21 and minus B22. So if you compare the coefficients, you are going to get that B11 is same as minus B11 and minus B22 is same as B22. For the other B12 and B21, you don't get any special relation. So what we have is that B11 equals minus B11. So B11, B22, these are all blocks, right, of B, and these blocks are of dimensions we have just decomposed B into by dividing the rows and columns into sizes M1 and M2, and these M1 and M2 are obtained by the division we obtained from A. right? The number of +1 eigenvalues and the number of -1 eigenvalues of A. Minus B22, right? So therefore we get that B11 equals 0 and B22 also equals 0. Now since B is also Hermitian, we haven't yet used the fact that B is a binary observable yet. So we have to now use the fact that first that B is a Hermitian operator. What we are going to get is that B12 and B21, they have to be transpose of each other. So B11 and B22 we have already seen they are 0 and B21 is same as B12 dagger. Okay. Now what's the second property of being a binary observable? The second property is that B square must be identity. Right? Only then we can assure that eigenvalues are all +1 and -1. So we have B square is identity, right? And so 0, 0, B12, B12 dagger square is identity. So let's multiply these. So B21 is now B12 dagger, that I'm assuming. And what you get is that B12 dagger 0, 0, B21 dagger is identity. So we get that, sorry, this is B12, right? This is B12 dagger, B12. And so therefore we have that B12 dagger. This is identity on, so B12 was of size. So this was M1, M2, M1, M2. Right? So this is going to have M1 rows and M2 columns. So B12 dagger B12 is going to be identity on M1 and B12 dagger B12 is identity on M2. Right? But now you see that both of these are now invertible matrices. And so what you will actually get is that B12 is an invertible matrix firstly, and it is a square matrix. So it's a B12 has a left inverse and a right inverse which is same, and so therefore B12 has to be a square matrix, which also means that M1 and M2 are going to be equal. So number of +1 and -1 eigenvalues of A have to be the same. So M1 has to be equal to M2. Firstly we have seen that. And we have seen that B12 is square and unitary, right? So this A matrix is now I and -I, okay? So which I can write it as Z tensor identity on M1. So M1 and M2 are now equal. And what I can do is that let C equals to B12, then in basis 1 up to M1 and C M1 plus 1 up to C twice M1. Under this basis, what we are going to see is that B will turn out to be equal to 0, 0, I and I, which equals X tensor I. So you have to verify this again. Okay, so you'll have to choose an appropriate unitary matrix corresponding to this basis, and then you'll have to check that this indeed holds true. You can refer to again the notes by literature Cleve, And here under this basis, what we'll see is that A is Z tensor IM1 and B is X tensor IM1. M1 and M2 are both equal, right? So here we have found such a basis, and this also proves the second lemma which we used in the last lecture. Right? So this completes the full analysis for the rigidity of CHSH scheme. We have proved all the lemmas also which we left earlier, right? So yeah, so this completes this section. Thanks. Bye.